All right, in this section we're going to look at polar coordinates, which is sort of a review for us, and then polar equations, which is kind of new to us. Okay, so you'll remember from pre-calculus that there are different ways to represent a point in a plane, and a coordinate system is just some kind of system that we use to represent a point. And we need an ordered pair of numbers. Those are called coordinates. And of course, the ones that we usually use are Cartesian coordinates. And the Cartesian coordinates, this is, defined by Descartes, and he decided that he would use two perpendicular axes labeled x and y, and then to say where a point is, we just do the distance from each axis. And so, here's the Cartesian plane. I have these two perpendicular axes, and then if I have a point, out here somewhere, the distance from the x-axis is 6, the distance from the y-axis is 5, and so we would call that 0.65. Okay, and it's all based on the distance that that point is from those two axes. Okay, so that's the coordinate system that we're used to and that we use most often. But we did a lot with the polar coordinates when we were in pre-calculus. Newton introduced the polar coordinate system. And in the polar coordinate system, we just choose any point in the plane and we call it O. So there's, okay, and we call that the pole. Also called the origin, O for origin. Okay, and then we draw a ray at the origin. Okay, and that ray, I'll put a little arrow on that so it looks like a ray for axis. And then when we define points, it will using an angle that has its initial side as the polar axis and then side elsewhere, and then we go along that terminal side and the distance from the origin along that terminal side to find the point P. So we have an angle and some value that's a distance along that terminal side of that angle, that where the point is in the plane. Okay, so the R value is the distance from the origin, and the theta is the angle that the line through the point makes with the polar axis. Okay. Very convenient for us to be able to convert, between these two. And in order to do that, I measured the Cartesian plane and plopped it right down on top of this one so that the origin of the Cartesian plane, intersection of the two axes, fell right on top of the origin of the polar plane. X-axis, the positive x-axis, lined up with the polar axis. Okay, so if we do that, okay, we get a picture that looks something like this. So in coordinate system, we would call the point x, y, because that's the distance. In the polar coordinate system, we would have to measure the angle the line through the origin and point P makes with the x-axis, which is now the same as the polar axis. Okay, and then we would have to measure that distance as well, and r theta, okay, would be the way to write it. So this one is the polar representation, and this one is the Cartesian. All right, so let's look at, or at least review, how we would go about graphing points in the Cartesian, in the polar plane. I had a straight edge here earlier, and now I've lost it. Okay. So let's say I wanted to plot the point 1, so that's my R value, and then 4. I'm going to call this point A so we can easily see where I've labeled it. Okay. So really, it's easy easily start with the angle first. So I would look on my polar plane, the angle 5 pi over 4. Okay, so 5 pi over 4 is right here. Okay, so I'll just use this for my straight edge. So this 5 pi over 4 along this line somewhere. Okay, so this from here go in this direction towards my marking of 5 pi over 4. That's my terminal edge. Okay, so I'm going to go along that terminal edge 1 unit from the origin. Circles out here, this shows me 1 unit, 2 units, 3 units, 4 units out from the origin. So here, and so there's my point A. And if we were to do point B, okay, 2 and then 3 pi, I would go, okay, there's pi, there's 2 pi, and these would be 3 pi. So the terminal edge would be right here. So there's my terminal edge. Okay. And then I need to go 2 units from the origin along my terminal edge. Here's the origin. I go out 1, 2, and the point would be right here. So that's point. Let's see, point C. Okay, so this time I need to go negative 2 pi over 3. Okay, so let's go, 2 pi over 3 is 120, so imagine I'm going back 120 degrees. So negative 2 pi over put me right here. So my terminal edge is right here. And then I'm going to go 2 units from the origin along my terminal edge. 1, 2 units, and I will be right here. And finally, let's mark point D. Starting with my angle 3 pi over 4. Okay, there's my terminal edge right there at 3 pi over 4. And now this one's a little bit tricky because I'm going to go negative 3 units from the origin. Okay, so far all of these have been positive, but so if I were going to go positive 3, I would go along this terminal edge. If I still want to go along the terminal edge, but I need to go in the opposite direction. So it's still going to be along this through to the other side. And instead of going, along the terminal edge here, this would be the positive direction. I need to go negative 3 from the origin. So 1, 2, 3. Point D. So it's along that same line that the terminal edge makes, but positive direction in towards the 3 pi over 4 marking. I need to go in the opposite direction, pi over 4 marking. Okay. So that would be how we would plot. Okay. And then hopefully we also remember from previous how to convert between them, but we will review that here. So we can of course make a connection, like I said previously, by just overlaying the Cartesian plane on the coordinate plane to make it so that the origins line up and that the polar axis coincides with the positive x. Okay, and then any point can be described with an xy coordinate or theta coordinate, and tell me what the same point is. Okay, so let's say we know, okay, we're going to use the r theta representation of it. So we find the associated x and y values. Okay, well, if we look at theta, let's think of as adjacent to theta, and r is the hypotenuse of this triangle that we've drawn. We could use the relationship that the cosine of theta is the adjacent x over the hypotenuse r. X is r cosine theta. And then to find the y value, well, y is opposite theta. So if we do the sine of theta, the opposite y over the hypotenuse of r, and so y is equal to r sine. Okay, so if I know the r and theta value, I just use the cosine of theta to get the Cartesian x-coordinate, and I do r times the sine of theta to get the y-coordinate. Okay, let's say we wanted to go the other direction. Let's say we knew what x and y were, and what r and theta are. Well, we can easily see that this is a right triangle, so we know that x squared plus y is r squared, and so that means r must be the square root of x squared plus y squared. Okay, and then to find the theta value, well, the y is opposite theta, the x is adjacent to theta, and so if we say of theta is the opposite of y over the adjacent x, and so if we solve for theta, we get that theta is the inverse tangent of y over x. Okay, so those will allow us to easily convert. You know, this is Cartesian, or sorry, polar to Cartesian, and this is Cartesian to polar. I'll go ahead and do that. So let's say we want to convert the point 2 pi to Cartesian. So it's in polar form. That means this is r and this is theta. Cartesian coordinates, well, Cartesian coordinates have an x and a y. Okay, so in order to find the x, we need to do r times the cosine of theta, and for this particular value is 2, and our theta is pi over 3. Okay, the cosine of pi over 3 is a half, so the x, and then we do r sine of theta. Y coordinate, r is 2, and then we need to do the sine of pi over 3. So that's 2. Sine of pi over 3 is square root of 3 over 2. So this will give us square root. Okay, so that means that the Cartesian coordinates of that point would be 1 square root. Okay. How about if we go the other direction where we know the Cartesian coordinates? Now remember, x and y pairs, and we want to write that in its polar form. So if we want a polar form value, and we need a theta. So our r value, we use the square root of x squared plus y squared. So in this case, that's going to be the square root of 1 squared, negative 1 squared. And so that's going to be the square root of 2. And to find our theta value, we're going to get the inverse tangent over x. So that's the inverse tangent of y, which is negative 1. So the inverse tangent of negative 1 is going to be of pi over 4. Okay, so our polar coordinate would be square root of 2 of pi over 4. Okay, and now if you think about coordinate, I'm going to go ahead and just, okay, so negative pi, like negative 45 degrees, so that's along this line right here. Okay, and then it's going to go out square root of 2 units, about 1.4. Let's say if, you know, that's 1, that's 2, maybe about right here. Okay. And so indeed we would have a 1, negative 1. Okay, the square root of 2 would be the hypotenuse. That's a 45, 45, 90 triangle. That makes sense. That's the coordinate. Okay, so one of the tricky things about polar coordinates is lots of different ways to represent them. So this is one of them, and that's the one that you'll get for using the formula. But sometimes, rather than using a negative angle, we would like to specify this point, but instead of negative pi over 4 angle right here. Okay, we'd prefer using the positive here. Okay, so if you think about what that would be, like that's just another way to get to that same side. It's a coterminal angle. So instead of using negative pi over 2, or sorry, negative pi, you could use positive 7 pi over 4. Okay, and that would get me to the same term, square root of 2 there. Okay, so that is sometimes the preferred representation because of both the angle and the R value are positive. To do it. The other way, you know, we also could put negative values here. So think about negative values side over here, but if we just extend that backwards back here, okay, and slide, but then go negative, then it'll go away from this into this one and put us at that point. Okay, so we use this angle right here with a negative square root of 2. Okay, and it would be 3 pi over 4. Okay, so probably one of those are the most desirable, but there is a fourth one, so we might as well. And that's if we go this direction. So, okay, so use both and a negative, and the negative pi over 2. So if we went in the negative direction, that would be 5 pi over 4. Okay, so all four of them are acceptable, and depending on, you know, what a kind of homework question might be asking you, they might, you know, want you to write values, or they might just, you know, accept the value you get by default from your equations. Okay. We'll talk about curves that are written with polar equations. Okay, so the graph of a equation. So a polar equation specifies r as a function of theta. Okay, and not with x's and y's. You know, we're used to y equals mx plus b, or x squared plus y squared equals r squared. Those are the kinds of equations we're used to graphing. But this, instead of y, okay, it has r and theta, because we're talking about a polar coordinate system. We're not going to put an x and a y in our equation. We're going to theta in our equation. Okay, so when we have an equation that has a function of theta, and we graph it just like we would in the cartoon, just make it a collection of all the points that satisfy the equation. Same thing with polar coordinates. It's just the collection of the polar points that satisfy the equation. Okay, so let's think about how an equation that's written in its polar form. All right, so we have the equation r. Okay, clearly r is a function of theta. Theta is not involved, but still it's a function. Involves, you know, r and or theta. So let's go ahead and just make a table of values, r and theta values, like we would if we were beginners graphing points. Make an XY chart and find some points. Well, we can make a, you know, R theta chart and find some points. Usually it's nice to pick the theta value first. So let's say we picked a theta value of 0. Well, if theta was 0, let's say we picked pi over 3. That's probably pi over 3. This is probably pi over 6. This is probably pi over 3. Okay, well, if it's pi over 3, then it's 2. Let's say we picked pi over 6. I'm just saying these backwards. Pi over 3. Okay, that's 2. Let's say we picked pi over 2. Well, then it's 2. Let's say we picked, well, then it's 2. Let's say we picked 3 pi over 2. No matter 2, right? Back to 2 pi, 2. Okay, so if we plot those points here, an angle of 0, and then going out 2 is here. Pi over 6 here. Pi over 3 going out 2 is here. Pi over 2 going out 3. And then we did pi and 3 pi over 2. Okay, so you can see we could have chosen these angles as well. 2, out 2, out 2. What we're really getting is just this circle, right? This radius of 2. So basically, we don't care what the angle is. We just want to be 2 units from the origin, is the circle centered at the origin with radius 2. So this is just the circle centered at the origin. Radius 2. Okay. So it looks like if we just have r equals and then some constant, what would the curve look like if we had theta in it? So this theta equals 1. Theta is an angle. So in this, we're thinking 1. We're thinking that's what that is. Okay. So again, once again, we probably want to little table of some r and theta values. Okay. And we know that no matter what, it's going to be 1. Okay, so maybe at, -2, at -1, at 1, at 2, maybe we can make this one 3. No matter what theta value, so no matter what our values, theta stays constant at 1. Okay, so in terms of plotting that is about how big is 1 radian, so we can put it on there. So if I radian, let's just go ahead and convert it to degrees so we can kind of figure out where it is. So to convert radians, to multiply by 180 over pi radians, the radians cancel out. So it's 180 divided by pi. Pi is a little bit bigger than 3, and so this value is going to be a little bit less than, okay, so this is a little less than 60 degrees. In fact, it's around 57 degrees. Okay, so here's 60 degrees is just before. Okay, so imagine, let me just put that 1. It's probably along. Okay, and so with, I would go -2 with that angle, so I'd go back to here, and I'd do -1 with that angle, back to here, 0 with that angle, that's the origin, 1 with that angle, 2 with that angle, 3 with that angle. You can see I could do, any value, all these values along this line, doesn't matter how far we go. Okay, any of those are values with that same angle, -1s, +1s. It's going to get this line. Okay, so we're going to get the line through the origin. Makes an angle of 1 radian with the polar axis. So that will be a straight line that makes a 1 radian angle. Okay, so this is perhaps more interesting because it has not just an r and not just a theta, but both. One is going to be just slightly trickier. It's not too hard, but it's going to be slightly trickier. Again, we're going to make a table that has theta and r. This time I put theta on the left side just because it's easier. Remember to go backwards when we graph our points. Okay, so 0 in for theta. Well, the cosine of 0 is 1, so this would give us 2. Pi over 6 in for theta. Well, the cosine of pi over 6 is square root of 3 multiply by that by 2, we get square root of 3, and square root of 3 is about 1.73. If we put pi over 4 in there, cosine of pi over 4 is square root of 2 over 2, multiply that by square root of 2. Square root of 2 is roughly 1.414. Pi over 3 is a half. Half of 2 is just 1. Cosine is 0. And then when we go into over 3, we're now getting into negative values. Okay, so the cosine of negative over 3 is going to be negative, because it's negative a half times 2. And then 4, that's going to be a negative square root of 2 over 2. So this is one's going to give us a negative 1.4. These are not negatives, these are approximately's. Approximately. 5 pi over 6, that'll give us a negative 1.73. Okay, and at pi, we're at negative 1 times 2, that's going to be 2. Okay. Alright, so let's just these on there and see what this looks like. So at 0, we're going to go out 2 there. At pi over 6, which is this line right here, we're going to go about 1.732. Okay, that's a little less than halfway between these two. Let me put it right about there. At pi over 4, which is this one right here, we're going to go out 1.4, 1.5, so it's going to be right before that. Okay, at pi over 3, that's this one, it's going to be at 1. At pi over 2, we're at 0. Okay, let's at 2 pi over 3, that's this one, is going to be negative. Go in this direction, okay, which is over here. 3 pi over 4, which is here, I'm going to go negative 1.4. There's here should be negative 1.4 is around here. And 5 pi over 6, which is here, I'm going to go negative 1.7, so I'm going to go, that's negative 1, negative 1.5, here's negative 1.7. Okay, and at pi, which is over here, I'm going to go negative 2, and I'm back. So if I tried to connect these, I mean, I have okay, it might so that's what the graph looks like for part A. And I'd say it looks maybe something circular in nature, maybe a circle. I don't know if my drawing's bad, maybe it could be an ellipse, we'll see. Okay, but let's go ahead and find an equation for this curve and, you know, see if it's something that we recognize, since it isn't necessarily perfect, and it's, you know, we're probably guessing it's a circle, but we want to know. So I have this equation, r equals 2 cosine of theta. Well, convert this to x's and y's. Okay, so some of the things that we know are that x is to r cosine theta. Okay, so solving that for we get x over r equals cosine of theta. If we ever see a cosine of theta in an equation, we could substitute x over r in for that. So equals 2 times x over r. You know, if we saw a sine, and we would want to use, sorry, you couldn't see that very well, huh? we could start with y sine theta, solve this for sine theta, y over r is sine theta. So if you ever have an equation with a sine theta invert, you could make that substitution. All right, so now we have this. If I multiply r to clear fractions, I'm getting r squared equals 2x. Okay. And then we also know that r equals the square root of x squared plus y. Relationship between r and x and y. So if I square r, I'm going to get x squared plus y squared. R squared here, I can substitute x squared plus y squared in for that. Okay. All right, so let's move everything over. X squared minus 2x. I'm going to leave myself a little bit of space and put my plus y squared over here. Okay. And when I have an x squared and a y squared in it is some kind of conic section for me to be able to see, it's a good idea to complete the square. So I'd want to add -1 squared to both sides so that I can factor this portion of it. So this is 1 squared plus y squared equals 1. Okay. So this is definitely the equation of a circle with center 1, 0 and square root of 1, which is just 1. So if we look at this, okay, 1, 0 here, that's the center of the circle, and then it goes out 1 unit, and apparently that is also 1 unit. It's harder to see that on a polar plane, but so you have a circle centered at 1, 0 with radius 1. Okay. This time we want to sketch the curve r equals 1 plus sine of theta. Okay, first of all, I'm going to graph this sort of as if it were like, okay, so this is going to be my theta axis and this is going to be my r axis. Well, if I treat it like a Cartesian equation, I know that this is just the sign shifted up. Okay, so it's going to have a center line at 1. Okay, and then up 1 and come down and hit the x-axis and come like that. So this would be at 0, at pi over 2. This would be at pi. This would be at 3 pi over 2 would be at 2 pi. Okay, so this will just help us figure out for various values what r is, because we can just kind of look at the graph and see what the value of r is, and then we can kind of put that appropriately onto the graph. Okay, and so what we see here is at 0 degrees, 0, then our r value is 1. 0 degrees, let's say this is 1. Let me try to all of these. Okay, so at 0 degrees, it's at 1. Okay. What we see is as we go from 0 degrees to pi over 2, what's happening is the r value is increasing from 1 to 2. Okay, so at pi over 2, it's going to be up here at 2. So it was 1, and as the angle is getting bigger and bigger and bigger and bigger and farther away until it gets to 2. Okay. So as this increases from 0 to pi over 2, r increases from 1 to 2. Okay, so we're right here. as theta increases from pi over 2 to pi, so as we're going from pi over 2 to pi, the r is going from 2 back down towards 1. So this is towards 1 as this is increasing to pi over 2. Okay, so when we get all pi, it's going to be at 1. So here's our terminal angle, and it'll be 1 unit. So it's going to be decreasing towards 1. All right, and then as the theta value goes from pi to 3 pi, you're thinking here's pi. So as it's going from pi to 3 pi over 2, so the basic. Okay, we're going to be going from 1 down to 0. So it's going to be going from 1 to 0, getting smaller. So it's going to be 0 when it gets to 3 pi over 2, and it's getting smaller and smaller and smaller. Or sorry, to 0. And then pi over 2 to pi, to 2 pi. Okay, so as we're increasing from 3 to 2 pi, our r value is increasing from 0 back up to 1. Okay, so when it gets to 2 pi, it'll be at 1, where we left off. That was our original spot. Increasing up to 2 over pi. So it looks like that. This is its polar curve. This would be the Cartesian version of it. Okay. So this has a special name. It's called void. Okay. Because it looks kind of like a heart. See, if you turn it upside down, it looks like a heart, and that hence the name Cartesian. Okay. All right, so we're going to end the video here and work on this, but that's a good warm-up and introduction to graphing polar curves.